School of Management Studies IGNOU presents an audiobook on the course MMPC 005 Quantitative Analysis for Managerial Applications for MBA program. Block 2 Probability and Probability Distributors. Unit 6 Discrete Probability Distributions.
After completing this unit, you should be able to understand the concepts of random variable and probability distribution, appreciate the usefulness of probability distribution in decision making, identify situations where discrete probability distributions can be applied, find or assess discrete probability distributions for different uncertain situations, and appreciate the application of summary measures of a discrete probability distribution. Introduction. In our study of probability theory, we have so far been interested in specific outcomes of an experiment and the chances of occurrence of these outcomes. In the last unit, we have explored different ways of computing the probability of an outcome. For example, we know how to calculate the probability of getting all heads in a toss of 3 coins. We recognize that this information on probability is helpful in our decisions. In this case, a mere 0.125 chance of all heads may dissuade you from betting on the event of all heads. It is easy to see that it would have been further helpful if all the possible outcomes of the experiment together with their chances of occurrence were made available. Thus, given your interest in betting on heads, you find that a toss of 3 coins may result in 0, 1, 2 or 3 heads with the respective probabilities of 1 by 8, 3 by 8, 3 by 8 and 1 by 8. The wealth of information presented in this way helps you in drawing many different inferences. After this information, you may be more ready to bet on the event that either 1 or 2 heads occur in a toss of 3 coins. This representation of all possible outcomes and their probabilities is known as a probability distribution. Thus, we refer to this as the probability distribution of number of heads in the experiment of tossing of 3 coins. While we know that our previous knowledge on computation of probabilities helps us in arriving at such representations, we recognize that the calculations may be quite tedious. This is apparent if you try to calculate the probabilities of different numbers of heads in a tossing of 12 coins. Developments in probability theory help us in specifying the probability distribution in such cases with relative ease. The theory also gives certain standard probability distributions and provides the conditions under which they can be applied. We will study the probability distributions and their applications in this and the subsequent unit. The objective of this unit is to understand a type of probability distribution, viz. A discrete probability distribution. Accordingly, after the initial presentation on the basic concepts and definitions, we will discuss as to how discrete probability distributions can be used in decision making. Basic concepts. Random variable and probability distribution. Before we attempt a formal definition of probability distribution, the concept of random variable, which is central to the theme, needs to be elaborated. In the example given in the introduction, we have learned that the outcomes of the experiment of a toss of 3 coins were expressed in terms of the number of heads. Denoting this number of heads by the letter H, we find that in the example, H can assume values of 0, 1, 2 and 3 and corresponding to each value, a probability is associated. This uncertain real variable H, which assumes different numerical values depending on the outcomes of an experiment and to each of whose values a probability assignment can be made is known as a random variable. The resulting representation of all the values with their probabilities is termed as the probability distribution of H. In this case, as we find that H takes only discrete values, the variable H is called a discrete random variable and the resulting distribution is a discrete probability distribution. In this situation, we have understood that the random variable takes a limited number of values. There are certain situations where the variable of interest may take infinitely many values. Consider, for example, that you are interested in ascertaining the probability distribution of the weight of 1 kilogram tea pack that is produced by your company. You have reasons to believe that the packing process is such that the machine produces a certain percentage of the packs slightly below 1 kilogram and some above 1 kilogram. It is easy to find that there is essentially to chance that the pack will weigh exactly 1 kilogram and there are infinite number of values that the random variable weight can take. In such cases, it makes sense to talk of the probability rather than the probability of the weight taking any specific value. These types of random variables which can take an infinitely large number of values are called continuous random variables and the resulting distribution is called a continuous probability distribution. Sometimes, for the sake of convenience, a discrete situation with a large number of outcomes is approximated by a continuous distribution. Thus, if we find that the demand of a product is a random variable taking values of 1, 2, 3 till 1000, it may be worthwhile to treat it as a continuous variable. Obviously, the representation of the probability distribution for a continuous random variable is quite different from the discrete case that we have understood. We will be discussing this in a later unit when we take up continuous probability distributions. Now coming back to our example on the tossing of 3 coins, you must have noted the presence of another random variable in the experiment, namely the number of tails, say t. T has got the same distribution as H. In fact, in the same experiment, it is possible to have some more random variables with a slight extension of the experiment. Supposing a friend comes and tells you that he will toss 3 coins and will pay you rupees 100 for each head and rupees 200 for each tail that turns up. However, he will allow you this privilege only if you pay him rupees 500 to start with. You may like to know whether it is worthwhile to pay him rupees 500. In this situation, over and above the random variables h and t, we find that the money that you may get is also a random variable. Thus, if h is equal to number of heads in any outcome, then 3 minus h is equal to number of tails in any outcome, as the total number of heads and tails that can occur in a toss of 3 coins is 3. So the money you get in any outcome is equal to 100h plus 200 into in brackets 3 minus h, which is equal to 600 minus 100h, which is again equal to, say, x. We find that x, which is a function of the random variable h, is also a random variable. This gives you the probability of you getting different sums of money. This may help you in deciding whether you should utilize this opportunity by paying rupees 500. From the discussion on this section, it should be clear by now that a probability distribution is defined only in the context of a random variable or a function of a random variable. Thus, in any situation, it is important to identify the relevant random variable and then find the probability distribution to facilitate decision making. In the next section, we will understand the properties of discrete probability distributions and discuss the methods for finding and assessing such distributions. Discrete probability distributions. In the previous section, we have learned that a representation of all possible values of a discrete random variable together with the probabilities of occurrence is called a discrete probability distribution. The objective of this section is to understand the properties of such distributions and discuss the methods for assessing them. In discrete situations, the function that gives the probability of every possible outcome is referred to in probability theory as the probability mass function, that is PMF. The outcomes, as you must have noted, are mutually exclusive and collectively exhaustive. Thus, we have learned that PMF is the name given to a discrete probability distribution, and if for any situation we can specify the PMF of the relevant random variable, the whole probability distribution is then specified. The properties of any PMF, say fx, where x the random variable, can be derived from the fact that fx basically refers to probability values. Any probability measure is by definition non-negative, that is, sigma fx equals to 1. Moreover, it follows from probability theory that fx equals to 1, the sum being taken over all the possible outcomes. Sometimes we are interested in finding the probability of a group of outcomes. In such cases, an addition of the relevant values gives us the result. Thus, in the example given earlier, we find that the probability of 2 or 3 heads equals to f into 2 plus f into 3, which is equal to 0.5. Further, we may be interested in the probability that the random variable will take values less than or equal to a particular quantity. The result in such situations is achieved by specifying what is known as cumulative distribution function or CDF. The CDF, denoted by FH, is found by adding the probabilities up to a given quantity, and it gives the probability that the random variable h will take a value less than or equal to that quantity. Assessment of the PMF of a random variable follows directly from the different approaches to probability that we have discussed in the earlier unit. The different methods by which PMF of a random variable can be specified are: number 1, using standard functions in probability theory; number 2, using past data on the random variable; number 3, using subjective assessment. We will now discuss each of the methods and the situations where these can be applied. Using standard functions. Sometimes the knowledge of the underlying process in an experiment helps us to specify the probability mass function. Probability theory has come out with standard functions and the conditions under which these standard functions can be applied to any experiment. Here we can find the outcome using Bernoulli process. Bernoulli process is defined in probability theory as a process marked by dichotomous outcomes with probability of an event remaining constant from trial to trial. In coin tossing, we find that the outcome of any toss is either a head or a tail, so that the dichotomy is preserved. Also, in each of 3 coin tosses, the probability of head or tail remains constant, namely 1/2. The probability distribution pertaining to such a process is standardized in probability theory so that we can directly write down the PMF corresponding to any experiment that satisfies the Bernoulli process. Such standard discrete distributions will be discussed in detail in a later section. Using past data. Past data on the variable of interest is used to assess the PMF only if we have reasons to believe that conditions similar to the past will prevail. The frequency of occurrence of each of the values of the variable are noted down, and the relative frequency of each of the values is taken as a probability measure. The basis lies in the relative frequency approach discussed in the last unit. You may like to compare the resulting PMF with the corresponding frequency distribution. Thus, under the assumption that buyer behavior has not changed much, we take the past sales data of a product to find the probability distribution of future sales. While frequency distribution is simply a representation of what has happened in the past, PMF represents what we can expect in the future. This method of assessing the PMF stems from the subjectivist approach to probability. This method is applied if there is no past data and the situation of interest does not resemble any known processes in probability theory. Suppose a record manufacturing company is contemplating the introduction of a new ghazal singer. Before introducing him, they want to find out the likely sales of record of the new person in the first year of the release of the record. The random variable here is the sales in first year. Let us denote it by S. We may here use our subjective assessment to find the PMF of S. One way to assess this may be, number 1, the company knows that currently 1 lakh people buy their records and it believes that out of this 1 lakh people, 20%, that is 20,000 customers, have the attitude to try anything new. So that, which means the other 80,000 will never buy an unknown singer's record in the first year of the release. They have also assessed that at least 10% of their customers are always ready for new ghazals. In other words, they expect the sales in the first year will be 10,000 with a 60% chance and 20% chance each that 15,000 or 20,000 people will buy it. We have understood the different ways to assess a discrete probability distribution. These distributions helps us in our decisions by presenting the total scenario in any uncertain situation. The PMF of sales are discussed so far and that may help the company in deciding how many records should be produced in the first year. While producing 10,000 records is definitely a safe thing to do, we realize that a 40% chance of not being able to meet demand is also there. Similarly, production of 20,000 records takes care of meeting all demands that may arise, but then there is a chance that some records may not be sold. Systematic analysis of such decisions can be done with the PMF and the relevant cost data and will be taken up in the Unit 8. Analysis is made easier if together with the PMF data, certain key figures of the PMF are presented. Thus, it may be easier for us to see things if the expected sales figure is given to us in this case. These key figures pertaining to a PMF are called summary measures. In the next section, we discuss some summary measures that are helpful in analyzing situations. Summary measures and their applications. As the name implies, a summary measure of a probability distribution basically summarizes the distribution through a single quantity. Just as we have learned in the case of a frequency distribution, here too we have the measure of location and dispersion that helps us to have a quick picture of the behavior of the random variable concerned. The objective of this section is to understand some of the summary measures and discuss the possible application of these measures. Measures of location. The most widely used location measure is the expected value. It is similar to the concept of mean of a frequency distribution and is calculated as the weighted average of the values of the random variable, taking the respective probabilities of occurrence as the weight. Expected value of a random variable gives us a measure of location and is an indicator of the long-run average value that we can expect. In the computation of the expected value, the most likely outcome is given the highest weight age. Sometimes it is useful to characterize the probability distribution by the most likely value, which is defined as the mode. The modal value is the value corresponding to which the probability of occurrence is maximum. Another thing sure of location that is of interest is known as fractal. A value hz is defined as the k fractal of the distribution of h if fh is less than k for all h is less than hz and fh is greater than equal to k for all h less than equal to hz. Measures of dispersion. Standard deviation or ST, range and absolute deviation are the measures of dispersion of a distribution. Of these, standard deviation being the most widely used will be discussed here. You may recall that the same term has been used in the context of a frequency distribution also. However, in a discrete probability distribution, we are dealing with a random variable and the distribution represents various values of the random variable that we expect will occur in the future. In such cases, the variance is defined as the expected value of the square of the difference between the random variable and its expected value. Then, SD is given by the square root of the variance. The knowledge on expected value and standard deviation of a distribution of a random variable is useful in our decisions. Suppose you have got an offer to take up any one of the two projects A and B. Both A and B have got uncertain outcomes so that the payoff for A and B are random variables. If expected payoff for project A is equal to that of project B and SD of payoff in the case of A is less than that of B, then you may decide to choose project A. Here, standard deviation summarizes the variability in monetary payoffs that we can expect from the projects. Some important discrete probability distributions. While examining the different ways of assessing PMF, we have noted that proper identification of experiments with certain known processes in probability theory helps us in writing down the probability distribution function. Two such processes are the Bernoulli and the Poisson. The standard discrete probability distribution that are consequent to these processes are the binomial and the Poisson distribution. The objective of this final section is to understand the conditions that characterize these processes and examine the standard distributions associated with the processes. This will enable us to identify situations for which these distributions apply. Bernoulli process. Any uncertain situation or experiment that is marked by three properties is known as a Bernoulli process. These three properties are: number 1, there are only two mutually exclusive and collectively exhaustive outcomes in the experiment. Number 2, in repeated observations of the experiment, the probabilities of occurrence of these events remain constant. And number 3, the observations are independent of one another. Typical examples of Bernoulli process are coin tossing and success-failure situations. In repeated tossing of coins, for each toss, there are two mutually exclusive and collectively exhaustive events, namely head and tail. We also know that the probability of a head or a tail remains constant, which is 1 by 2 from toss to toss, and result of one toss does not affect the result of any other toss. Similar dichotomy is preserved in testing of different pieces of a product. Each piece, when tested, may be defective or a failure, or non-defective or a success. We know that the production process is such that the probability of a non-defective in any trial is P and that of a defective is Q, which is equal to 1 minus P. Once the process has stabilized, it is reasonable to assume that the success and failure of each piece is independent of the other, and also the probability of a success or P or a failure Q remains constant from trial to trial. Thus, it satisfies the conditions of a Bernoulli process. The random variables that may be of interest in this situation are: number 1, the number of success or failure in a specified number of trials, given the knowledge on the probability of a success in trial. This implies that if the experiment is observed n times, then given that the probability of a success is same for any observation, we are interested in finding out the distribution of number of successes that may occur in n observations. Number 2, the number of trials needed to have a specified number of successes given the knowledge on the probability of success in any trial. We are interested in finding out the probability distribution of the number of trials required to get a specified number of successes. The binomial distribution and the Pascal distribution provides us with the required PMFs in these two cases. Poisson distribution is applicable to events occurring randomly over time and space. This PMF has been used widely to represent distributions of several random variables like demand for spare parts, number of telephone calls per hour, number of defects per meter in a bale of cloth, etc. In order to apply this PMF in any situation, the conditions of a Poisson process need to be satisfied. A Poisson process corresponds to a Bernoulli process with a very large number of trials n and with a very low probability of success, that is m by n in any trial. Consider the occurrence of any uncertain event over time or space in such a way that the average occurrence of the event over unit time or space is m. We may take the number of accidents occurring over a time period with m denoting the average number of accidents per month, or we may be interested in the number of defects occurring in a strip of cloth manufactured by a mill with m denoting the average number of defects per meter. For each of such situations, we see the possibility of dividing the time or space interval into n very small segments such that within a small segment the conditions of the Bernoulli process hold. Thus, 1 month can be divided into say 30 into 24 into 60 intervals of 1 minute each, so that the probability of occurrence of an accident in any minute is equal to m over 30 into 24 into 60 and reduces to a very small quantity so that there is almost no chance of having 2 accidents occurring in 1 minute. The independent property of the Bernoulli trial also holds true here, as a 1 minute interval basically corresponds to a trial. This enables us to calculate the probability that R accidents will occur from the Poisson formula. The mean and variance of a Poisson distribution are equal and are given by m. This property is sometimes used to check whether the Poisson applies for the event under study. Now let's summarize the unit. We have introduced the concepts of random variable and probability distribution in this unit. In any uncertain situation, we are often interested in the behavior of certain quantities that take different values and different outcomes of the experiments. These quantities are called random variables, and a representation that specifies the possible values a random variable can take together with the associated probabilities is called a probability distribution. The distribution of a discrete variable is called a discrete probability distribution, and the function that specifies a discrete distribution is called a probability mass function or PMF. We have understood situations that give rise to discrete probability distributions and discussed how these distributions are helpful in decision making. The concept and application of expected value and other summary measures for such distributions have been presented. Different methods for assessing such distributions have also been discussed. In the final section, certain standard discrete probability distributions and their applications have been discussed.
We were listening to the audiobook by the School of Management Studies IGNOU for MBA program, course code MMPC 005, Quantitative Analysis for Managerial Applications. Course Coordinator, Professor Anurag Saxena, School of Management Studies, IGNOU. Voiceover by Harpreet Kaur. Edited by Uday Sharma. Program assisted by Tarannum Jahan and Jagbandhu Jana. Program produced by Dr. Manoj Kumar Singh. This program was brought to you by Electronic Media Production Center of Indira Gandhi National Open University.